let's continue our discussion into relativity. Right? We won't derive these results. Okay, but let's talk about relativistic momentum. Relativistic momentum. Okay, so we know about Lorentz transformation. We know about how velocity is transformed. Okay, we know all these things. Right now, we need to get a notion of relativistic momentum. Right, and our clue, the clue that we have is that whatever momentum is, okay, it's the good thing about momentum in Newtonian mechanics is that it is conserved. Momentum is a conserved quantity. Right, so if it's conserved in one frame, it has to be conserved in another frame also. Right, so momentum has to be conserved. Now, if you look at particle collisions and use relativistic velocity, etc., you will see that if momentum is conserved, you have to define it as gamma mv, not as mv, but as gamma mv, where gamma is 1 by square root of 1 minus v square by c square. Right? P is equal to gamma mv. Right? So this is the relation for momentum. Right? Now, in some notation, as I said, which I'm not following, but I want you to be familiar with it. Some notation, they simply write it as gamma m0v, which is equal to mv. And this m they call as gamma m0, but this is completely unnecessary. Okay? Sometimes people do it. So P equal to gamma mv vector. This is the relativistic momentum, right? And we can also talk about relativistic energy. Relativistic energy. Now, relativistic energy also has to be conserved in collisions. Energy also has to be conserved, right? Or we can find it using the work energy theorem, and you will see that the conserved quantity in collisions, all right? Conserved quantity that has the dimensions of energy in collisions, if we use relativistic relations, is gamma mc square. Okay, it's not mc square, it's gamma mc square. Is gamma mc square, is not mc square, right? What's the rest energy? So if you look at this, all right, this we can write it as mc square divided by square root of 1 minus v square by c square. Okay, now this is approximately equal to, let's say, okay, let's write one more step. This is equal to mc square 1 minus v square by c square whole raised to minus 1 by 2. Am I right? Now we can use this binomial expansion, okay, and take the first term. So we say this is approximately equal to mc square plus, okay, mc c square, and sorry, yeah. Just write one more step. This is approximately equal to mc square 1 plus v square by 2c square. Okay, now this is equal to mc square plus half mv square, right? And there are higher order terms. Okay, but when velocity is small, this is enough. Okay. So you get back the Newtonian expression for kinetic energy, and there's an extra contribution here. This is known as the rest energy. Rest energy, all right? So E rest or E0, okay, there are different notations for this, is equal to mc square. Right? That's the rest energy. So total energy includes kinetic energy and rest energy. This is just for the Newtonian case. So you can write the kinetic energy, relativistic kinetic energy, you can write it as relativistic kinetic energy. You can write it as gamma mc square, that's the total energy, minus the rest energy, right? Minus the rest energy, right? So this is relativistic kinetic energy for a free particle, right? Relativistic kinetic energy is gamma mc square minus mc square. Is this fine? So this can be asked sometimes. All right. Now this is a good thing. We see that E rest, this 0 means that it's at rest. E0 or E rest is equal to mc square. All right. This is the definition for mass actually. Mass equal to E0 divided by c square. All right. Okay. Or E rest. I'll write it as rest just to emphasize this. Right. So what is mass? It's the energy content of an object when it is at rest. Right. Mass is the energy content of an object when it is at rest. That's the definition of mass. That's the best definition for mass that we have. That's the reason why we don't need this relativistic mass thing. Right. By definition, mass is the energy when the object is at rest. Right. So you don't need to so when you talk about a relativistic mass, this definition doesn't work. Right. So this is the best thing you can remember. Remember, mass is not E by c square, but E rest by c square. Right? Rest energy divided by c square. Right? Okay. So this is the reason actually why you can also see this relationship coming up. If you look at the mass of the protons or mass of nucleons, right? So just an example. If you look at the mass of nucleons, Nucleons means protons. We have got protons, neutrons, etc. All right. Okay. We know now that these protons and neutrons are made up of quarks. Okay. Quarks have masses, right? Quarks have mass. Right? Quarks are massive. It has a small mass. Okay. There are also gluons, which are particles that carry the force between them, but these are massless. Gluons are massless. Okay. Now, naively, you would imagine that the proton mass is equal to sum of the mass of the quarks. Right? It's the sum of the mass of quarks, but it is not true. It is much I think proton is UUD. Am I right? I think it's all right. So you will see that much of the proton mass comes from the energy of this particle. So, for example, the energy of the gluons. All right. So that's how the total mass of an object is equal to the. So that's how you see that the energy contributes to the mass. All right. This is a dramatic place where this comes up. Okay. You'll see that you add the mass of all the quarks, you will see that it's much less than the mass of the proton. So where does all the mass of proton come from? The best idea is that it comes from the energy of these gluons, which are moving at a high speed. Okay, gluons themselves are massless. Okay, this also means that if you have a box, of particles which are moving, right? The particles are moving at very high energies, right? And you will see that the mass of this box, right? The mass of the box would be equal to the mass of this box, and then plus the energy. Right, there will be a contribution to this mass due to the energy of these particles also. Okay, right. But this is called the rest energy of the box itself, right? Even though it consists of some energy moving parts. You can talk about the total mass of the box, and there will be also energy contributions to it. Right? So there is a way in which energy and mass are fundamentally related. Okay, that was Einstein's realization. Right? We'll be using these formulas, and there's another thing called the energy momentum relation.
Relativistic kinetic energy gamma mc square minus mc square.
Yes.
And negative.
We know that this gamma mc square is the total energy. Okay, this is equal to rest energy plus kinetic energy, right?
Okay.
So you see that rest energy is mc square.
Yes. Kinetic energy relativistic kinetic energy.
Yes. Gamma mc square minus mc square would give you just the energy due to the movement.
Okay.
All right. It can be asked, but it may not be useful except in problems, but you have to know this, right? The relativistic total energy includes this rest energy contribution also. So if you need the kinetic energy alone, you have to reduce that from the total energy. Okay. Right. And we got this clue by looking at the non-relativistic limit. Okay. If V is less than C, we saw that gamma mc square goes as mc square plus half mv square. Right. This is the kinetic energy term. Newtonian kinetic energy. You see that there's an extra term in the relativistic thing. This is known as the rest energy. So if you need the kinetic energy, you just subtract it from subtract the rest energy from the total energy. All right. Okay. So relativistically, there are higher order terms on V square. There are higher order terms on V square. Okay. Is that fine?
Oh, fine.
Okay, that reminds me of something else. I forgot to tell this. So we have got E is equal to gamma mc square. Okay, and we have got P is equal to gamma mv. Right, that's the momentum. So if you just look at this, you see a nice relation. You see that P vector by E is equal to this gamma and gamma n gets cancelled. This V vector by C square. Is that correct? Just divide P vector divided by C vector by C square. So you see that V vector is equal to C square multiplied by P vector divided by E. Is this fine? Is this correct?
Yes.
This can be used in problems, all right? Sometimes the energy and momentum are given, and you might be asked to find the velocity, right? Or you may be able to find energy and momentum easily, and then you can find the velocity. This is the easiest way. This is the easiest way. If the energy and momentum are given, this is the easiest way to find the velocity of the particle. All right, you can do it in different roundabout ways. You can use some other relations and get this v outside of this gamma and solve for it, but this is the easiest way. Okay, so it's a good thing to keep in mind. We also have this energy and momentum relation. We can obtain it easily. We see that E is equal to square root of P square C square plus M square C raised to 4. Right? This is an important relation. Now this relation, instead of this, if you have E equal to gamma MC square, we talk often of particles which have mass 0, like photons. Right? We can talk about neutrinos, which have a very small mass. Okay, almost mass 0. So you can talk about particles of mass 0, and then you cannot use this relation, right? You cannot use this relation. Okay. One reason why we cannot use this relation is this: gamma is 1 by square root of 1 minus v square by c square. All right. So you see that when v is equal to c, if the particle is massless, it moves at the speed of light. If the particle is massless, if it has to exist, it has to travel at the speed of light. Okay, otherwise, it doesn't exist. So all massless particles travel at speed of light. So if v equal to c, then this term blows up. This is not a nice thing if mass equal to 0. But this will get a 0 by, what do you say, 0 by 0 or something like that. It's not good. Okay. But if we can use this relation, if mass is equal to 0, you see that m is equal to 0, then E is simply Pc, right? The energy is equal to, we can find the energy from the moment. It's equal to P multiplied by C. So if it has a momentum, it has an energy. If it has a mass, it has an energy. All right. Okay. Okay. Now, the nice thing about relativity, okay, we study relativity from a different angle so far. The nice thing about relativity is that it actually identifies the quantities which are not relative. Okay, when we say relative, people tend to think that everything is relative, right? You see that time is relative, velocity is relative, length is relative, all right? And is everything relative? No, actually, relativity identifies, okay, actual absolute quantities. Right? There are absolute quantities. Not everything is relative. There are absolute quantities, and we'll from time to time we'll get used to some of these absolute quantities. Some of them we have to memorize. They can be asked directly. Right? And one such important quantity is this combination. Okay. Okay. So we'll do it as a problem. We'll do it as a problem. Which among the following? Which among the following is a Lorentz invariant quantity, which means it does not change when you make a Lorentz transformation. Lorentz invariant. Okay, I'll write it as differentials. In terms of differentials here, we have got first option is this. You look at this combination, all right? C square dt square plus dx square plus dy square plus dz square. Okay. Now I want you to look carefully at this thing. We know this dx square plus dy square plus dz square. Right? This is the spatial separation between 2 points in space. Am I right? If you have got 2 points in space, okay, and if this is dx and this is dy, then this distance is ds square equal to dx square plus dy square. Am I right? If it's 3 dimensions, we will have dx square plus dy square plus dz square. Okay. Now this looks like a quantity which is 4 dimensional. Instead of dx, dy, and dz, you also have a c dt, right? Instead of dx square plus dy square plus. So we know that we can extend Pythagoras theorem, dx square plus dy square. In 3 dimensions, it becomes dx square plus dy square plus dz square. In 4 dimensions, we can say that this becomes, if c dt is one of the coordinates, right? Why do we have a c here? So that the dimensions are equal, right? Now c dt has dimensions of length, dx, dy, dz also have dimensions of length. All right. So we can imagine, okay, is this the geometry of space-time? Right. We'll see these things in detail. So is this quantity Lorentz invariant? Right. That's one question. This is just, this equation is just direct generalization of Pythagoras theorem to 4 dimensions. right? Direct generalization of Pythagoras theorem to 4 dimensions, all right? We know that this is a length and it's invariant under rotations and all that. So we also have this quantity, c square dt square minus dx square minus dy square minus dz square. And we have this quantity minus c square dt square plus dx square plus dy square plus dz square, right? And the question goes like this. The question goes like this. Option A, 1 and 2. Okay. Option B, 1 and 3. Okay. Option C, 1 and 2. Option D, 2 and 3. Okay. So obviously from the options, or we can also take an option E, which says 1 only. Okay, you can have more options like 2 only. Something like that, right? Which option is the correct one?
2 and 3.
Yeah, 2 and 3 are invariant. This can be easily checked. This can be easily checked. You don't have to believe me. You can just apply the Lorentz transformations in here, and you will see that this quantity is not invariant under Lorentz transformation. Right? You can check this is not invariant under Lorentz transformation. But if you look at this quantity, right? If you look at this quantity, let's check this quantity. Okay. All right. So this quantity is not Lorentz invariant. It means that the Pythagoras theorem cannot be directly generalized to 4 dimensions. All right. If this is a geometric quantity, then it has to be invariant under coordinate transformations. Like length remains the same even if you rotate the coordinate systems. Right. So this means that this is not the geometry of spacetime. If spacetime has a geometry, it's not Euclidean. Right. This kind of geometry is known as Euclidean. And if spacetime has a geometry, this says that it is not Euclidean because this is not invariant. Right. This is not invariant. We'll see these things in detail. So let's check this quantity. All right, we'll see that. Let's say ds prime square is equal to c square dt prime square minus dx prime square minus dy prime square minus dz prime square. Right now you apply the Lorentz transformations used for dt prime, dx prime, and dy prime and dz prime. Again, we assume that it's moving along the x-axis. So dy prime and dz prime do not change. Right? What happens to this dt prime square? This becomes dt prime is equal to we have this relations dt prime is equal to gamma
dt minus vx by c square.
Yeah, dt minus vx by c square. Right. Yeah, let's write it like that. So we have got this gamma square. I think I can pull outside. Okay, gamma square, and we have got dt minus vx by c square. I've just applied the Lorentz transformations, all right, in the differential form. Dt minus vx by c square minus what about dx prime square? That's gamma square multiplied by what's the dx prime? Dx prime is equal to gamma dx minus v dt. Is that correct? Yeah, v dt. Okay. Dx minus v dt. So it's gamma square dx minus v dt square, right? And you have got dy prime is dy, dz prime is dz. Okay, is that fine? Okay. Now it's just a question of squaring and adding. So you just square this thing. This is c square gamma square. Okay, let's pull gamma square outside. That makes it easier. So this is c square. Square this thing, it's dt square plus c square, and there's a c raised to 4 there. So this is, it pulled gamma square outside, all right? So the square of this is v square x square by c raised to 4, cancels with this c square, and then we get v square x square by c square, right? And there's a cross term minus, right? 2 dt vx, c square and c square get cancelled. Is that correct? But I just squared this, okay? This and pulled this c square inside. So this is c square dt square plus c square v square x square by c raised to 4, right? So c square get cancelled, and minus 2 dt vx by c square, and c square get cancelled, right? And we have pulled this gamma square outside. We have pulled this gamma square outside. This is a possible question, and this quantity is very important. Okay, I've done it as a problem, but we'll see the importance of this quantity as we move on, right? So this is minus 2 dt vx, and we have got gamma square is pulled outside. We have got minus, this is, okay, there's a minus there, dx square minus v square dt square, right? And then the cross term comes with a minus, but this minus makes it plus, so it's plus 2 dx v dt, okay? And we have minus dy square minus dz square. Immediately see that these two terms get cancelled, okay? All right, and what else do we have here? So let's write this as gamma square, and we pull the c square dt square outside, all right? dt square, there's a dt square here and a dt square there. We just combine it and write it as c square minus v square, okay? And here we have got plus, oh, I think I missed this dx, right? Dx, is that correct? Dx, right? Yeah. Okay, so that is dx square multiplied by 1 minus v square by c square, right? I've just combined these terms, minus dy square minus dz square, okay? All right, so this c square can be pulled outside here, and then this becomes 1 minus v square by c square, all right? So you can write this as gamma square multiplied by, okay? And you can pull this 1 minus v square by c square outside, and you get c square dt square minus, it's minus here, okay? Minus dx square, it's a minus here, right? Because this, yeah, this quantity is plus, okay? And we've got a minus here. So if you pull minus dx square outside, you get 1 minus v square by c square, right? And then minus dy square minus dz square. And what's this quantity? This is simply 1 by gamma square, right? Because gamma square is 1 by 1 minus v square by c square. So these two terms this cancel, and you get c square dt square minus dx square minus dy square minus dz square. So this quantity is called ds square, and this is Lorentz invariant. If this is Lorentz invariant, the minus also, okay, you just multiply it by a minus, then, or we can say ds square, this is equal to ds prime square, or we can look at the minus sign, ds, or we can, or some other quantity, we'll call it also as ds square. This quantity is also invariant. Just multiply it throughout by a minus sign, and the minus sign does not change when you make a Lorentz transformation. So this quantity is also invariant. Okay, so you will see that the other quantity is not invariant. Okay? Now, what's the physical interpretation of this quantity? Let's look at the physical interpretation of this quantity. This is a very important quantity. Right, we'll come to this thing later on. But what's we'll follow this. All right, we'll take this thing. And this ds square, sometimes some books say that this is ds square, some books say that this is ds square, right? So if you take particle physics books, they usually use this convention. If you take some general relativity book, they usually use this convention, right? It doesn't matter, both are relativistically invariant, all right? The real physical quantities out of it, if you take this ds square is equal to c square dt square minus dx square minus dy square minus dz square, okay? Now this, if you pull this c square dt square outside, c square dt square outside, this is equal to 1 minus, okay? This becomes dx square plus dy square plus dz square divided by dt square, am I right? C square dt square. Yeah. Okay. Now, what is this dx square plus dy square plus dz square by dt square? This is nothing but the velocity. If it's one dimension, dx by dt is the velocity, right? So this is the distance traveled. This is the distance, spatial distance traveled in a time dt, am I right? Dx square plus dy square plus dz square is a spatial distance traveled. You can also write it as dr vector dot dr vector, right? Dr vector by dr vector dot dr vector divided by dt, right? Because dr vector is dx I cap plus dy j cap plus dz k cap. Okay, so if you square it, you will get dx square plus dy square plus dz square. So this is nothing but dr vector dot dr vector. Am I right? Okay, and this is dt multiplied by dt. So dr by dt is the velocity. So this is v vector dot v vector, and that is v square. Is that fine? So this is equal to c square dt square 1 minus v square by c square. Is this clear? Okay, is this step okay?
Okay.
All right. Now what is this quantity? You see that this c square is there. If you take ds square by c square, this is equal to dt square 1 minus v square by c square, or this quantity is often called as d tau square. Okay, ds square by c square is often called as d tau square. That's equal to dt square 1 minus v square by c square, or d tau is equal to dt square root of 1 minus v square by c square. What is this? We already saw from Lorentz transformation the relation of this form. Delta t equal to delta t0 divided by square root of 1 minus v square by c square. Okay, from here is that delta t0 is equal to delta t multiplied by square root of 1 minus v square by c square. Is that clear? So this thing, okay, this is actually the proper time. Delta t0 was the proper time. It's related. This is the coordinate time. This is called the proper time. Right. So d tau is the proper time. It's the proper time. So what's important of ds square? Okay. For particle trajectories, this gives you, all right, the proper time interval between two events. We'll discuss this in more detail. But the important thing we see here is that we know that ds square is invariant. Okay, we know that c is invariant. So this combination is also invariant, right? C is Lorentz invariant, d square is Lorentz invariant. So you see that d tau is a Lorentz invariant quantity. So that's why we say that the proper time is Lorentz invariant. Okay, proper time is Lorentz invariant. Okay, now what does this mean actually? We can think of a space-time now. We can think of a space-time. Okay, ct and x. I will suppress the other coordinates, but we can think of space-time. The points on space-time are called events. Okay, and you can take any path. Imagine any path between these 2 points in space-time, right? And you just take this path, a small part of this path, and you can find d tau, right, corresponding to it using this relation. Okay. What's this d tau actually? I said it's the proper time, which means that it's the time on a clock. Okay, time elapsed on a clock which is moving from this point to this point. Am I clear? Okay, this suppose we have got 2 points in space-time and we want to find d tau. All right. We said that d tau has the interpretation that it's the proper time. D tau has the interpretation that it's the proper time. What's the proper time? Proper time is the time measured on a clock which is at rest on that side. Right? So in this case, this proper time gets a slightly interesting meaning. The proper time here is the time elapsed on a clock which is moving from this event to that event. Okay, time elapsed on a clock which is moving from A to B. All right. So that's the proper time. All right, and that's a Lorentz invariant quantity. It's very important that it's Lorentz invariant. Okay, you will see, and this ds square is called as the invariant interval. Okay, invariant interval. Okay, and it is actually a measure of what you call as a distance between 2 points on space-time, or distance between 2 events. All right, distance between 2 events. I don't say distance in the usual sense. It's a different kind of distance. So it's a distance between. We have a notion of distance which is invariant. All right, we'll build upon this. Right? This is the key to the geometry of special theory of relativity. Okay. All right. Any questions? So in this part we have just seen the relativistic energy, relativistic momentum, all these things, and we have introduced a new quantity for, okay, it seems that this particular combination is Lorentz invariant. So we look at this combination and we see that this interesting thing has a very interesting property, that it's Lorentz invariant and it's associated with the proper time. It's associated with the proper time between 2 events. Okay. So if you need the proper time between a whole lot of events, all right, there are so many events there. If you need the proper time, what you do, you take the proper time d tau for every interval and then integrate. So you'll get the total proper time. So you can ask this question: what's the time elapsed on a clock okay, traveling from A to B along this path. Okay, what would you do? Just take d tau for every every small section, and then just integrate, add all of them up, and that would give you the time elapsed on a clock that's traveling from A to B along any path. Okay, all right. So that gives you the measure of length. So in a way, clocks can be used to measure distance in space-time, right? Clocks can be used to measure. We'll elaborate on this. Clocks can be used to measure distance in space-time. Right? If this is a notion of distance and the clock traveling from A to B gives you the proper time from A to B, then we can use clocks to measure the distance between A and B. Okay, this is very similar to an odometer. You know, if you go by a bike or a car, you'll have this thing which shows you the distance that you traveled, okay? 30 kilometers, 40 kilometers. So that's known as an odometer. Okay, that's known as an odometer. Okay, odometer is a thing to measure distance. You might have used some sort of app when you walk, okay, how much distance you have walked, or you can see this in your car or bike, right, or in your bus. Okay, this odometer tells you how much distance you have traveled. Right, in the similar way, clocks tell you how much distance you have traveled on space-time. Right? Clocks give you the distance traveled in space-time. Odometer gives you the distance traveled in space. Clocks give you the distance traveled in space-time. All right, and we'll elaborate on this in the next class. Are there any questions? Anything?
No, sir.
Okay.
Thank you.
Thank you.
Thank you, sir.